you shine right into either of your eyes, both of your eyes have to constrict. What happens if either of your eyes does not constrict? Let's find out. Hello ladies and gentlemen, welcome back to my YouTube channel, Neurosketch with Again. Today we got to discuss about pupillary white reaction. We got no time to waste. Let's dive into it and let's talk about it. Oh yeah. So what happens when you look into eyes of your friend? You try to look into the eyes of your friend, and you will see like you are seeing a picture, a small picture of you in this part over here. In this part is what is known as a pupil, and it's where you see yourself when you are looking into eyes of your friend. And so it's known as a pupil because a pupil means a little person. It's where you see yourself. So it's like you are seeing a smaller version of you when you're looking to eyes of a friend, and that's how the name was derived. This is Latin name. It's coming from Latin name pupus, which means a boy, which now translates into little person, and it's like where you see yourself when you are looking to eyes of a friend. So it's known as a pupil. So a pupil, I mean, for us to discuss about pupillary white reaction, we really need to know what the pupil is, because yeah, that's how we will know everything about the pupil. Well, we are not talking about all other structures of the globe of the eye. We have separate videos, but for convenience we have at least to know what a pupil is before we discuss the pupillary white reaction. So pupillary white reaction, we are talking about how your pupil respond to how does it respond to light and to different level of illuminations of light. So to begin with, we start to know what a pupil is. So a pupil is just a gap. It's a defect that is left by an iris. So it's I want to show you. This is an iris. An iris, and an iris has got it is a muscular, something like a muscular realm, and it has got a gap. It has got a hole in it, a defect in it, and that defect is what we call a pupil. The primary function of a pupil is to control the amount of light that gets into your eye. So it controls the amount of light. So whether you need too much light to go through your retina, through your eyes to the retina, the pupil will direct, and whether you don't need too much amount of light, it will constrict to reduce the amount of light that goes through the eye. But as you can see here, the pupil is just a gap, and it's a gap within the iris, so it's controlled. The size of the pupil is controlled by these different muscles of the iris. This is why you say it is controlled by an iris. The pupil is nothing, like it's a hole, it's a gap, it's nothing. So it's not something structural, it's just a hole that is left. So we have this is an iris now. This is an iris, layers of the iris, muscles of the iris. So we have got two muscular layers of iris, or the muscles of the iris. We have got this we call the circular muscle, because it's in circle, it's in circle. And then we have got these radial muscles here, the radial muscles, because they radiate, you see, they radiate away. So we have the circular muscle and the radial muscle. I believe you discussed about this when you are high school in biological science. There is like this description: circular muscle and radial muscles. And now see, this circular muscle, when it contracts, it's like coming to decrease this diameter of the pupil. So the circular muscle, it contracts to decrease the size of the pupil. So when it contracts, it's goes together. It goes together to constrict the pupil. So now you can guess this is the radial muscle. When the radial muscle contracts, it will pull the pupil away. It will pull the circular muscle away from each other. By doing so, the diameter of this gap here increases, and the diameter of this gap, the gap is the pupil. So the diameter of the pupil increases when you pull in the radial muscles. So we've got two new terminologies, two new names. We have got the dilator pupillae because it dilates the pupil. It dilates the pupil, the dilator pupillae. And then we have got the sphincter pupillae because it constricts the pupil. When it contracts, it pulls together the pupil, the other muscles, so it decreases the size of the pupil, and that's what we call the pupillary constriction. Where the radial muscle, it pulls away the circular muscle, so it increases the diameter of the pupil, the diameter of the gap, and the gap is the pupil, so it increases the diameter of the pupil, so it dilates the pupil. It dilates the pupil. So these are the two terminologies that we're using. But we nowadays, we have to use the sphincter pupillae and dilator pupillae. The sphincter pupillae and dilator pupillae. I mean, you are right if you say a circular muscle and radial muscle, but it would be super nice if you use these terminologies, dilator pupillae and sphincter pupillae, for matter of convenience. All right, so we are out of control of our, pupil size. We are out of control means it's something that is controlled automatic, and it falls under our autonomic nervous control, autonomic nervous system. It is controlled by autonomic nervous system. We are out of control of our pupils because we don't decide whether or not to dilate the pupil. We don't decide whether or not to constrict. It's something that occurs automatically. So when you are exposed into different levels of illumination of light, well, the pupil will react into that environment, and that reaction is what we call either the pupillary light reaction or the pupillary dark reaction. Pupillary light reaction or the pupillary dark reaction. So we have said already, the sphincter, the function of the sphincter pupillae is to constrict the pupil to decrease the size of the pupil. And when does this happen? It happens when you are exposed into too bright light. So when you are exposed in a bright light, your pupil will constrict because you don't need that too much light to go through your eye. Otherwise, remember, too much bright light can damage. You remember now? It can damage your retina, the photoreceptor area. Remember, you have to go back and watch the previous videos. Yeah, so the pupil decreases the size because we have too much light. And when you expose now into dim amount of light, you need to utilize the little amount of light that is available to get a better vision. So what happens is you dilate your pupil. So your pupil dilates. It dilates so as to utilize the little amount of light that is available, and that's what we call dilator pupillae. And I think it makes sense. When I'm saying that it's under autonomic control. We do exactly nothing to control the size of our pupils. We do exactly nothing to control the niente. All right. So, as we've said, the sphincter pupillae will constrict the pupil, and the dilator pupillae will dilate the pupil. The sphincter constrict, and the dilator pupillae dilate. So, what are the reasons that your pupil will dilate other than being exposed to too bright of light? Assume you have an optimal amount of light, but at certain situation your pupil will dilate, and at a certain situation your pupil will constrict, but you are exposed in you keep the amount of light constant. So assume you are in a jungle. Remember how we made to survive in Kingdom and Maria? Okay, this is another way. So assume you are in a jungle and you see an hungry lion coming from afar. Is coming towards you. What happens? You have said you have the pupil size is autonomic. It's under autonomic control. So what happens when you see a lion? Between sympathetic and parasympathetic, what do you think will be activated when you see the lion? So think about what makes you fight or flight. So that would be your sympathetic. Okay. So that would be your sympathetic. So the sympathetic is activated when you see like you are in fight or flight mode. So when you see, now you have seen the lion is coming. So what happens in your pupil? Does your pupil constrict or dilate? Does it constrict or dilate? Because you want to take much actions. You don't want to take like appropriate actions, whether to fight or to fight. So your pupil will dilate so as to like get enough amount of light coming from the lion or from that dangerous stuff, so that you take appropriate action. So now the parasympathetic will be activated to direct your pupil. So the sympathetic, the one that decides you to fight or to be fright, will be activated to direct your pupil. So the sympathetic directs your pupil, and yeah, so that's a sympathetic. And again, what do you think? The parasympathetic obviously now you constrict the pupil, because why? The parasympathetic, you don't need is rest and digest stuff. So it's a rest and digest. While you rest and like you about to fall asleep, do you really need to have a dilated pupil? No, we don't need. So the parasympathetic will constrict the pupil, and sympathetic will dilate the pupil. Sympathetic will dilate the pupil. So that's how we say, because they are under autonomic control. So we have got new terminologies that we can use. So the pupillary dilatation, is also known as mydriasis. Mydriasis is for pupillary dilatation, and meiosis is for pupillary constriction. So mydriasis for pupillary dilatation. So if you now you're solving some clinical questions or scenarios, and you find like something mydriasis, that's a pupillary dilatation, and meiosis is also a pupillary constriction. So as we've said, we dilate the pupil in response to dim amount of light, or we can also dilate in response to sympathetic stimulation. For example, you see it's a sympathetic fight or flight. So I think you know more about that. And then where do we get this sympathetic now? The sympathetic, this is also called the dark reaction, pupillary dark reaction, because it's how your pupil respond into dark environment. So it's a pupillary dark reaction. And the parasympathetic, as we've said, it constricts the pupil, and that is what's known as meiosis. And this reaction, or the reflex into when you're exposed to light, is known as the pupillary light reaction. So we've got this all of these terminologies. And then we know that the sympathetic is coming from superior cervical ganglion, and parasympathetic is coming from oculomotor. Let me emphasize this in this slide here, and this slide. So we have said it's under autonomic control, so it's either sympathetic or parasympathetic. And we all know now, we're now conversant that dilatation is the sympathetic, and constriction is parasympathetic. All right. So we know that the parasympathetic system is craniocaudal, is craniosacral. This means, we have a separate discussion discussing our autonomic nervous system, but just as a hint is that if you say that a nerve has got the parasympathetic fibers, this parasympathetic fiber can either come from cranium, brain, or the sacral portion of the spinal cord. So it's a craniosacral. There is nothing from cervical spinal cord all the way to the lumbar spinal cord. There is nothing like parasympathetic coming from there. There is nothing like that. So we are not surprised that the oculomotor nerve, cranial nerve number 3, will carry the parasympathetic fiber to the pupil so as to constrict the pupil. No worry about that, no doubt about that, because the oculomotor nerve is coming from the head, from the brain, from the cranium. So it's a cranial part of the, parasympathetic. No worry about that. And then the sympathetic is, thoracolumbar. Thoracolumbar is found from, the spinal cord. There is nothing like sympathetic in your head. So there is no like sympathetic ganglion. There is no anything like a ganglion. And you know what a ganglion is now. There is nothing like a ganglion. This is sympathetic ganglion in your brain. So it's either coming from the cervical all the way to the lumbar part of the spinal cord. So it's known as the thoracolumbar. We have a separate discussion about that, don't worry. But what I'm surprised is now we don't have the sympathetic in the head, but the pupil is in the head. How does it get there? How does the sympathetic get into the eye? How does it get into the eye? So think about it. 1, 2, 3. All right. The sympathetic is, the sympathetic into the eye. It's got a majestic, appearance. It's majestic presentation. It's like just like how young Dar es Salaam young Africans get into the pitch, so they get majestic. So we have majestic presentation of the sympathetic fibers. See, they are coming, we say they come from the superior cervical ganglion. So we have this one is known as the superior cervical ganglion. I mean, we have a lot of ganglions, but the most proximal, the most superior above is the superior cervical ganglion, because we have said the sympathetic is found in the sympathetic chain, which is running from the cervical spinal cord all the way to the lumbar, but we don't have anything like sympathetic in the head. So it comes from here. But how does it get now to the eye? This is how I'm calling it. I said it's majestic because it is carried by the internal carotid artery. It is carried by the internal carotid artery. So it is not carried by like something like a nerve. There's no nerve that goes to the eye. No, it is carried by the internal carotid artery, So the origin of the sympathetic is coming from the superior cervical ganglion, but gets into the eye by the way of the sympathetic, by the way of the internal carotid artery. How majestic, how majestic it is. So it's so like it is a unique presentation. It's a unique transport. It's a unique transport. It goes by the way of the blood vessel. So it's so unique. Yeah, so if we get something like damage to in this superior cervical ganglion means we will have damage the sympathetic that goes to the eye. So we have like a constricted pupil. So we will not be able to dilate the pupil. So the pupil remain constricted. Well, we see about some I will make a separate video to discuss about this pupillary pupillary some different disease of the pupil. You can say the disease of the pupil. So you will find it out. So that is it from the sympathetic and the parasympathetic. Now let's discuss about the pupillary reaction. So the pupillary reaction is the reaction of the pupil in response to light. The reaction of the pupil in response to light. It's how your pupil respond to different level of light. So when you shine light, as I've said, when you shine light into either of your eyes, either one, so both of your eyes have to constrict. So if I shine here, all of them have to constrict. If I'm shining here, all of them have to constrict. And if I'm shining to both of your eyes, all of them have to constrict. So let's see a pathway, a pupillary reaction, a pathway of the pupillary light reaction. So when you shine light into your eyes, where the information goes to the retina as usual, and then from the retina the information is carried by the optic tract, the optic nerve. The optic nerve, it goes then from nasal retina and the temporal retina, the information you will cross at the optic chiasm, and then from optic chiasm we'll go to the optic tract. Now we see we have bilateral, because this is temporal, this is nasal. We have bilateral, and then from bilateral it goes. We said, remember when we said in the previous video, we said we have the extrageniculate pathway that's something that deviates, or something that bypass the lateral geniculate. So from the lateral geniculate, from optic tract fibers, some of fibers we say we go to the superior auriculus, remember, so superior auriculus, and some will go to the pretectal nucleus, some will go to the pretectal nucleus. And we say all of these pretectal nucleus and the superior auriculus, they are found in the brainstem, the midbrain, which is a part of the brainstem. And then so this is the extragenucleate. The other time we discussed how the information goes to the visual cortex, and today we are not talking about the visual cortex, because we said, like, a bigger part of the brain is devoted to deal with the visual information in different stations. So today we are talking about these stations around here. All right, so so the information now that it lays after getting into the so-called the pretectal nucleus in the midbrain, and after it gets to pretectal nucleus in the midbrain in both eyes. You see now we had like a fiber crossing here, and then we had another one maintained in the same side, so that we get like a stimulation of both pretectal nucleus. So from pretectal nucleus we have multiple crossing over. We have multiple crossing over, and this will lead into different presentation when it comes into defects of the pupil, of the pupillary reaction. Well, so from pretectal nucleus, the information will go to the Edinger-Westphal nucleus of this side and this side. So we see we have we have a multiple crossing. So information after getting here, it goes to this pupil, to this Edinger-Westphal, and from this the same pretectal nucleus goes also to the Edinger-Westphal of the other side as well. Again, we had another information coming from this side, so this one also from this pretectal nucleus will go to the ipsilateral Edinger-Westphal and the contralateral Edinger-Westphal. So you see already we have like almost three crossing over. And then now the information from the Edinger-Westphal, again, you see that this is another crossing over that's about to happen here. So information from Edinger-Westphal nucleus will also go to the either side of the eye, to the either eye. So you see we have a fiber here, the fiber is crossing over to supply this eye, and another fiber is maintained to go through the same eye, go through the same eye. What does it mean? This is to say we have an afferent information through the optic nerve. We have afferent information through the optic nerve. In other words, the optic nerve is afferent fiber. It carries the afferent fiber, and when it goes to all of this nucleus, the information is carried back to the eyes by the way of the cranial nerve number 3. The cranial nerve number 3 is known as the oculomotor nerve. So it goes back by the way of the oculomotor nerve. So we have afferent fibers which are carried in the optic nerve, and then we have efferent fibers which are carried within the oculomotor nerve, which is cranial nerve number 3. Cranial nerve numero 3. All right, so I think now it kind of makes sense to you. And now, the information out from where it goes for it case, it case the parasympathetic, preganglionic parasympathetic fiber, and then they go to synapse at the ciliary ganglion, and then at the ciliary ganglion, after ciliary ganglion, now we have the postganglionic parasympathetic fibers. So I think you pause the video and try to digest this one, because after this is when you can now take different pathologies of the pupils, of the reaction of the pupil in response to light. So why when you shine light into one eye, both of your pupils have to constrict? It's because of this multiple crossing over here. You see, from the pretectal nucleus, the information will go here and here, and then assume we have damage at the pupil at the pretectal nucleus of this side, the right pretectal nucleus. What happens? what happens, this left pretectal nucleus, it also it projects into the left to the right Edinger-Westphal nucleus as well. So it like compensates, even if this the pretectal nucleus of this side doesn't work, where there is no problem at all, because this one is gonna like compensate. It sends other information to the Edinger-Westphal nucleus, and we assume also this Edinger-Westphal nucleus, it doesn't work, so we don't like this one is not functioning, the pretectal nucleus, and this one does not function as well. Well, if it doesn't function or work, the information from here will go to the Edinger-Westphal at this point, and then from this Edinger-Westphal, the information will go on either side of the eye, on either eye. So there is no problem at all if we have these two nuclei not functioning. This is why when you shine light into your eye, one eye, both of them have to constrict because of this multiple crossing over of information between these two nuclei. So it's like made into to respond at different levels. So let's see different pathologies now. Okay, so we have something that we call the direct and indirect pupillary light reaction. I'm telling you something simple to grasp at this point. The direct pupillary light reaction is when you shine light into this eye and then you observe the pupil reaction into the same eye. Direct. I'm shining direct into this, and so I'm observing changes in this eye. When I'm shining light directly to this eye, but I'm observing this eye over here, because we have said already, like both pupil will have to constrict. So when I'm shining light in this eye and then I'm observing at this eye, that is known as indirect pupillary light reflex, indirect pupillary reaction, and the indirect one is also known as consensual light reaction, consensual light reaction, or indirect light reaction. We have a lot of questions that kind of asking the consensual and the direct pupillary reaction, and we will need your knowledge about these two parts. So let's see like different presentation of different pathology when it comes to pupillary light reaction. So case number one, assuming now, I think you guys now know like the afferent fibers are carried within the optic nerve and the inferent fibers are carried within the oculomotor nerve, like cranial nerve number 3. So optic nerve is cranial nerve number 2, and the oculomotor nerve is cranial nerve number 3. Okay, so what happens if we have damage at the cranial nerve number 2, the optic nerve, the afferent? Every reflex, you know what a reflex is, So every reflex has got a afferent fiber, processing neurons, a nuclei, the nuclei that process or neurons, and then it has got the efferent fibers. Now, when we like have damage on a afferent fiber, which is the optic nerve, what happens? Think. Like what I mean here, what happens is in response to the pupil. What with this pupil constrict or direct, and then what about this? Will it constrict or direct? So this is what I mean. So what happens when you have like damage the optic nerve? Think about it, optic nerve, and remember we are shining light into only one eye. We are shining light into this eye only. Forget about this one. So we are shining about this, and then we are checking the response to this eye and this eye. So think about it. 1, 2, 3. I think you've like had enough time to think about. And then what happens here is we are shining the light from this eye, and remember when we say like if you have a total blockage of optic nerve, when we completely broke the optic nerve, the completamente broken the light ray, is like we have like 100%, 100% no right information that will go through that optic nerve. So what happens is there is nothing like stimulation of all these nuclei. So will this eye constrict? The answer is no. What about this? Will this one constrict? No, because there is nothing to stimulate the nuclei. So there is nothing like pupillary constriction when you have damage the optic nerve when you are shining light at the same eye. So this one will take information, I mean it would like stimulate all other neurons, and then we would see the effect, but we can't see the effect because the optic nerve is damaged. So what about second case? Well, what is this, guys? Oh, sorry. What is this? Yes, this is the oculomotor nerve, which is cranial nerve number 3, and the oculomotor nerve, which carries the parasympathetic to the eye. It's a afferent fiber of the pupillary light reaction. So what happens if you have damage of the parasympathetic of afferent fiber? Number one, we know, right? Okay, so the light there, you have shown the light to this eye. So the information will be carried by the way the optic nerve, and then it goes all to these neurons, to this nucleus. So the information from here will go to the either side of the pupillary reaction. But we have broken the output to the eye, output from the nuclei to the eye. So will this eye constrict? The answer is no, it does not constrict, because we have broken the output fiber that will come to constrict the eye. So well, it got the information, and the nuclei responded by constricting the pupil, but we have got a problem over here. We have a situation, and so there is nothing like reaction in this eye. What about this one? Will it constrict? The answer is yes, because we've got nothing like outflow obstruction to this eye. So this eye will constrict, and this one will dilate. So the direct pupillary reaction will be negative, like we don't have reaction on this eye, but the consensual, when you're looking to the other eye will constrict. So we see like we have a constriction of this eye, and then this one does not constrict due to different pathology. So think about the third example. So you are shining light into this eye, and then the light information goes all the way to all of these nuclei, and then from the nuclei now the information will go on either side, on either eyes, So this one is broke, this one is not. So will this pupil constrict? Think. Yes, it will constrict, because there is nothing like obstruction. So from the Edinger-Westphal nucleus, the information go the way to constrict the pupil. What about this side where there is nothing like constriction, because we are broken, completamente broken, 100%, and there is no pupillary reaction on this eye. So think about another scenario. So assume we have like broken the optic nerve on the other side. Remember, we are shining light into this eye, and the information is carried by the way of the optic nerve to all these nuclei, and after multiple crossing of these fibers, the information now has to go back to the eye. I have to go back into either eyes to constrict, and when it goes back, it uses the oculomotor nerve and not optic nerve. So will this eye constrict? For sure, yes, it will constrict, because there is nothing like broken, and all the the nuclei are intact, all the nuclei are good. What about this? Will this one constrict? Think about it. 1, 2, 3. Write me in the comment. Case number 4, write me in the comment. I know most of you, when I'm telling you to write in the comments, you don't write, and I want you to write in the comment. I want to know how you think about that. So write me in the comment what happens when I have damage to this optic nerve of the other eye. What happens into the side of the pupil. So the knowledge of the pupillary reaction is very, very important to assess the brainstem functioning, the functioning of the brainstem. As I've just told you, the nuclei, the Edinger-Westphal nucleus and the pretectal nucleus, they're all found in the brainstem, but specifically on the midbrain. Remember when we dissected the midbrain? So they are found in the midbrain. So if we don't have the pupillary reaction, I mean, we can have what can I say? How can I put? So if we don't have the functioning pupillary reaction, we can have pathology all the way through the pathway to the center. But if we have bilateral pathology now, we say like sudden onset of bilateral loss of pupillary reaction. You see how rare is it to get a bilateral loss because of multiple crossing, multiple crossing. So yes, we can have damage on either optic nerve. Well, that's another possibility. But we can have also the damage to the the nucleus, the processing center, which are found in on the brainstem, midbrain of the brainstem. And so we like do the pupillary reaction every now and then to check the size, to check the status of the brainstem, the brainstem. But as we know, we can maybe we can have some pathology that will affect the bilateral pathway, and then we'll spare the nuclei. I think you understand what I mean by the nuclei, the Edinger-Westphal and the pretectal nuclei. So we can spare, maybe we can spare them, and then we have bilateral pathology, but that's very rare. When we find like both pupils are not like reacting to light, both all of them, then you shine light to this eye and then you shine also to the other eye, there is nothing changing, maybe we can have the central pathology in the brainstem. And then this is why now remember the diagnosis of brain death, we had a lot of reflexes, and one of it, the pupillary reaction or pupillary reflex, is to check the function of the brainstem, because the brainstem is the one that controls the vital functioning of the body, like respiratory and cardiac functioning. But also, if you are a fan of, if you watch any kind of movie, and when you see that someone wants to confirm someone is alive, the immediate thing that he does is to shine the light into the eyes to see how, when the pupil if the pupil respond. If the pupil respond, then you know, like, the brainstem is functioning well. So this person is potentially alive. But even though if we find that like a person does not constrict the pupil, maybe we can have other pathologies. We can't say the person is dead based on the pupillary reaction. We need to also assess all other functioning, other brainstem reflexes, and we have a separate discussion about all of this. But we know sometimes the pupil are affected by some medications. So some medication, for example, atropine, it dilates the pupil. So the pupil will be like fixed and dilated. So assume we find someone maybe has got a motor traffic accident, for example, and maybe this person, now if you shine the light, you say that the pupil do not react to light, they remain dilated. So we are not sure of the medical history of this person. Maybe he or she has got something like atropine. Maybe she attended eye clinic a few days ago, because this atropine can have 2-week effects. So it can have a half-life of 2 weeks. So even if I applied atropine yesterday or 2 days ago, my pupil will still be dilated. So you find me in a motor traffic crash, and then you shine light into my eyes. You say my eyes are not responding, and then you say and then you're saying I am dead. Well, I am not dead. I am not dead. You have to go and check for other brainstem reflexes. This is why it's important. Of course, it's a quick screening method, but it's a quick screening method to know if a person is alive or not. But it's not confirmatory. It does not confirm if someone is dead. This is what I'm trying to tell you. So the size of the pupil can also be affected by different medications, and that's a separate discussion. So do you know that the two pupils are not exactly the same? They are not exactly the same. So we have a degree of discrepancy in the size of the pupil. So the left pupil and the right pupil, they are not completamente, they are not exactly esatto 100%, the same. They are not the same. The size are not the same. We have a small degree of discrepancy, and that's what we call anisocoria. Anisocoria is the slight decrease, discrepancy in terms of the size of the pupil. The human body is not a perfect symmetrical, and we also know that the breast, for example, when you, I don't know if you know about this, but the two breasts they are not 100% the same in terms of the size. So that if you pay a close attention, we know that we have a slight discrepancy between the two breasts. and that's how we human are made, because we are not perfectly symmetrical, so we have some degree of discrepancy in different in different body parts. So that is it from today's discussion on pupillary reaction, and don't forget to subscribe, because I've got a million contents, a million things to talk to you, a million of some of the neglected topics, like an elephant in the room. So we have a lot of neglected things that we will discuss together. So the only way you and I keep in touch is by subscribing. So make sure you have subscribed and hit the bell icon, and you will stay tuned. Until next time, alla prossima, ci vediamo.